Hello everyone, my name is Anis El-Gibli. I'm a postdoctoral researcher at the Center of Wireless Communications in University of Oulu in Finland. Today I will be presenting our paper entitled Layer-Wise Federated Group Alternating Direction Method of Multipliers for Communication Efficient Decentralized Deep Learning. This is a joint work with Sabir Ahmed and Mehdi Benes from the Center of Wireless Communications in University of Oulu, and also with Jihong Park from Deakin University in Australia. As we all know, machine learning is a key enabler for beyond 5G applications. In beyond 5G, we are aiming at up to 99.99 reliability and less than 1 millisecond latency to support applications such as autonomous driving. Unlike 5G URLLC, which used to rely on short packet transmission, and beyond 5G, some applications must simultaneously support high data rate and massive number of connections. As an example of such applications is autonomous drone swarm in a rescue mission, which requires not only URLLC, but also a massive number of wireless control loops for inter-drone collision avoidance. With that, we are moving from URLLC to extreme URLLC or next generation predictive URLLC, which leverages the recent advancement in machine learning to enable highly accurate prediction of traffic, states, and other key metrics. This is a good paper about extreme URLLC. Now I describe some challenges in training machine learning models. The first challenge is the lack of data samples at a single entity, and that's due to the fact that data is generated at the edge devices. Therefore, it's distributed by nature, and shipping the raw data to the cloud raises the following issues. First, it may violate the data privacy. It also may introduce a large latency and large amount of communication overhead, which becomes a big challenge under limited communication resources, calling for communication efficient and data and privacy preserving distributed machine learning algorithms. Here I describe some schemes that have been proposed to allow communication efficient and privacy preserving distributed and decentralized machine learning, and I also propose our solution. Those algorithms that have been proposed to ensure privacy and to ensure communication efficiency, they do not allow sharing the raw data. Instead, they either allow sharing the gradient vector per learning iteration or the model itself. I will start with federated learning. Federated learning, as we can see from the figure, is a server-based scheme where at every iteration, every worker performs one or several local operations. For example, every worker could be computing the gradient with respect to a global model that has been downloaded from the server using a randomly selected mini batch of data, or it could be performing a number of local SGD iterations. In this case, when it's computing the gradient, then every worker will share the gradient with the server. In case of performing number of local SGD iterations, the workers will share their models with the server. Then the parameter server performance one global computation step. It could be one global SGD iteration if the server receives the gradient vector, or one model averaging step if the server is receiving the models. In our prior work, we proposed FGADMM. It's a decentralized algorithm. I'm not going to go into the details of FGADMM. For the details, you can check this paper, and you can also watch this video in this link. I will just explain it in high level. In a nutshell, FGADMM solves this optimization problem. As we can see from this constraint, every worker except the first and the last one has a joint constraint with only two neighbors, the right and the left ones. With that, what we did, we divide the workers into two groups, head group and tail group. At every iteration, first of all the head groups, all the workers in the head group update their models or their primal variables in parallel, since they do not have any joint constraints. And then every worker will share its updated model with its two neighbors from the tail group. Then every worker in the tail group will update its model, and it will do the same. It will share its model or its primal variables with its two corresponding neighbors from the head group. And after the primal variables are updated, then every worker will update the dual variables locally. In this paper, we extend JDMM to allow for the deep neural network architecture, where we don't really enforce the constraint here to be in the whole model. So we can do per layer consensus. So the two workers that do not need to be agree in all of the layers. They could be agree in the models or the weights of subset of the layers. And we also account for the stochastic data sampling, where at every iteration, like the federated learning, at every iteration, a randomly selected mini batch of data is used to update. And we also allow for a number of local updates before sharing the outcome with neighbors. Moreover, we allow we give different time periodicity to different layers. For example, the small layers can be shared every T local iteration, where the large layers we can share them every beta T iterations, where beta is greater than 1. So when we share the large layers less frequently, we significantly reduce the communication overhead per iteration. Now I describe the steps for updating the primal and the dual variables at iteration k plus 1. As I mentioned in the previous slide, first of all head workers will update their models in parallel. This is the augmented Lagrangian function at iteration k plus 1. The nth worker will use the kth version of its left and right neighbors and the kth version of the dual variables to update its own model. Since in deep neural network, this problem cannot be solved in closed form expression, we perform a number of local iterations, and then after this number of local iterations, the head worker will share its outcome with its two neighbors from the tail group. And then every worker in the tail group will update the same way, except that every worker in the tail group will use the k plus 1 version of its right and left neighbors from the head group. So the head workers are always one step ahead of the tail workers in terms of updating their primal variables. After that, every worker will update the dual variables locally. Now I describe the simulation results. For the data set, we used MNIST data set, which is images for handwritten digits from 0 to 9, as we can see in this figure. For the neural network architecture, we used two architectures, multi-layer perceptron and convolutional neural network. As we can see from these two tables, for MLP, we considered 6 fully connected layers. The first layer has the largest number of weights, accounting for about 82% of the total number of weights. For CNN, we considered this architecture where we have 3 convolutional layers and then 2 fully connected layers. The first fully connected layer, layer 4, has the largest number of weights and accounts for more than 97% of the total number of weights. We conducted experiments using 4 workers and 2,000 samples. We distributed them equally across workers. We considered 3 variants for federated JDMM. We refer to them as 1x, 2x, and 4x. What we mean by that, first of all, in 1x, every layer is shared at every iteration. And when I say every iteration, I mean every global iteration. So at every global iteration, every worker still runs number of local iterations to update its local model. So when we say 1x, then every layer is shared at every iteration. 2x means every layer except the largest layer is still shared every iteration, but the largest layer is shared every other iteration. And for 4x, the largest layer is shared every fourth iteration. So as we share the largest layer less frequently, we are reducing the communication overhead per iteration. Now I describe the simulation results. I will start with the conversion speed. We compare all variants of federated JDMM with federated learning and standalone. In standalone configuration, every worker is trained using its local data set. There is no collaborative learning in this case. As we can see from these two figures, all variants of federated JDMM have much faster conversion speed compared to federated learning. Now we compare the algorithms in terms of the accuracy. We see similar results. After a few iterations, we see significant increase in the accuracy of federated JDMM compared to FL. For example, for MLP setting, after 20 iterations, federated learning accuracy was around 30%, while it's more than 80% for all variants of JDMM, federated JDMM. When we let all the algorithms run for 100 iteration and then report the accuracy, the testing accuracy numbers, here we see some numbers here for CNN and MLP configurations. For example, for CNN, the 1x configuration for federated JDMM, where we share the largest layer every iteration, has the highest accuracy. Then it comes after that, the 2x configuration and the FL, they have the same accuracy. So here, when we share, when we reduce the number of times, like when we share the largest layer less frequently, we see a slight drop in the accuracy, but there is a huge saving in the communication by just reduce the number of times we share the largest layer. As we share the largest layer less frequently, we see a drop in the accuracy. Of course, there is a saving in the communication, but that comes at the cost of less accuracy. Therefore, there is a trade-off here between the communication and the accuracy. We see here the lowest accuracy is when every worker, of course, here there is no communication at all. So we save in communication, but we pay a high cost of low accuracy or low testing accuracy. So standalone has the lowest accuracy compared to all of the algorithms. And we see the similar behavior for MLP setting. Now we compare all the algorithms in terms of the communication efficiency. We measure the communication efficiency by the total energy consumed in 100 iterations. We assume every element in the model vector needs 32 bits to be transmitted. We performed 1,000 experiments. Every experiment we randomly drop for workers in 100 by 100 meters per grid. All other bandwidth and power parameters as shown here. We plot the complement CDF of the communication energy cost. As we can see from these two figures, federated JDMM performs much better in terms of saving the communication energy compared to federated learning. And that savings can grow significantly larger than federated learning as we allow to share the large layer less frequently. To conclude, layer-wise federated JDMM achieves faster conversions, higher accuracy, and lower communication costs as compared to federated learning. I would like to also mention that we have been working in other extensions for JDMM, such as quantized JDMM, where every worker quantizes the model before sharing it. So we reduce the payload size per channel use. We also have been working in another extension of ADMM called Federated ADMM, where all workers can access the bandwidth non-orthogonally, and we allow workers to train over analog communication system motivated by the fact that the parameter server is interested in the aggregated output of all workers, not the individual value of every worker. To know more about these two works, you can check these two papers. With that, I would like to thank you for watching my video. And if you have any questions, please don't hesitate to email me. Thank you.